Matthew Conlen from University of Washington, like Jessica, that we had earlier. And his first job in data visualization was to design a bracket about March Madness for 538. Some of you may know the American media, 538. And his last job is hopefully as fun as the first one. That's what he said. Very good. Thank you, Matthew.
Thank you. All right, so I'm Matthew Conlen. I'm a PhD student at the University of Washington. This talk is called Towards Design Principles for Visual Analytics in Operations Contexts. I just want to start off by kind of unpacking that a little bit. So design principles, I think, are important for kind of providing guidance for designers about kind of when you're building a dashboard or a visual analytics system, not what you should do exactly, but these are the things that you really should be thinking about and considering. And here's kind of like, you know, we've seen lots of systems do this before, and so you're probably going to want to take these things into consideration. And design principles like this exist and have existed for a long time, but not for particular domains. And so in this talk, I'm kind of talking about the domain of operations. And what I mean when I say operations is things like if there's kind of an emergency or some sort of crisis happening, where do you send the resources? Where do you send your people? If you're the Coast Guard, where do you put your boats? If you're designing a factory, how do you lay out the assembly line? Where do you put the workers and things like this? And the last one is spacecraft systems operation. So if you're NASA and you have to tell a satellite where to go or tell a rover where to go, how do you do this effectively? And the thing that kind of all of these have in common is that as an analyst working in these contexts, you're going to have to make a decision. You're going to have to make a decision quickly, and you're going to have to take kind of multiple scenarios into account. So there's kind of risks associated with these things because you're not really totally sure what the outcome is going to be, but you kind of want to consider this level of uncertainty across these different things. And so these principles that I'm going to be talking about are kind of motivated by work that I did over the summer, this previous summer with NASA Jet Propulsion Laboratory. So we designed a system for telecommunications engineers who are working with the Opportunity rover, which is a rover that's currently on Mars. And basically the problem that we had to solve was, can you help us optimize how much data we send back from the rover to Earth? And this thing has been on Mars for a long time, over 10 years now. And it has recently suffered hard drive failure, and so every night it has to go down for a nap and kind of power off. But the problem is that when it does this, it loses all of its data because of this failure. So anything that we don't send back is just lost, and it's kind of science that we it's just in the void, and we could have collected it, but we didn't. And so this task of optimizing how much data we can actually transfer back became really important recently because of this. There's actually quite a number of variables that go into play in this situation for kind of how do you drive the rover in such a way that you maximize the data that can be sent back. There's a handful of satellites that are in orbit around Mars, and so as an analyst, as a telecommunications analyst, you have to choose one of these to say, okay, today I'm going to use this satellite, I'm going to beam the data to this one, and then that's going to relay it back to Earth. All these satellites have different orbital geometries. So kind of the path that they take through the sky is going to affect how much data can be transferred, because it could be kind of a shallow path, it could be kind of very straight up and down, and kind of the amount of time that you can sort of have visibility between the rover and the satellite affects how much data can be transferred, which kind of is somewhat intuitive, I think. There's other things that go into play, such as the surrounding terrain. So if there's a mountain blocking your view, you can't send data during that sort of period of the overpass of the satellite. The rover has a lot of the rover has a lot of instruments on it, and these instruments can also include kind of the path between the antenna and the satellite, which will cause it to not be able to send as much data. And finally, there's kind of the shape of the terrain that the thing is sitting on. So if it's on a hill, it's going to be pointed kind of off to the side, and the antenna is not going to be pointing straight up, and so this is also going to affect how much data we can actually collect. right? And so what the analyst actually has to sort of decide at the end of the day, every single day, they have to say, okay, here's where we're gonna park. Here's kind of the direction that we're gonna park it in, and here's which satellite we're gonna use. And the reason that we're talking about direction is kind of that corresponds to, like, if we're on a hill, we know how that affects where the antenna points. And so we kind of incorporated this idea of a top-down view of the rover that corresponds to a direction a lot in our system. And so in the system, you see these polar plots coming up quite a bit. And the polar plots, they kind of correspond to, okay, there's some data straight up. This corresponds to if the rover's pointed straight ahead, it's sort of 0 degrees. There's some data on a slice over here, and this is corresponding to, you know, the rover having been turned. And at each of these positions along the polar plot, we're displaying 3 values. We're displaying this background color, this kind of blue that you're seeing, and that represents how likely is it that we can actually make a connection to the satellite. So this is an independent variable from how much data can we transfer. So first of all, we have to make sure, okay, we can actually connect. And then the 2 lines that you're seeing, the kind of red and purple lines, correspond to 2 different estimates of the same value, which is how much data we think we can transfer.
Darker blue is better, or?
Yes, darker blue is better. So darker blue is, we're confident that we can make a connection there. And then with the 2 lines, the purple and the red lines, we want it to be out to the edge of the circle, because that means we expect to have a lot of data. And we want those 2 lines to be close, because that means our 2 models, they sort of agree, and we're doing two different ways of calculating this value. Yeah.
What's the antenna type of the rover?
I think it's a UHF antenna, but I'm actually not a telecommunications expert, but it's UHF, and it's directional. And okay, so this is kind of getting into the actual system that we built. So this is the screen that you see when, as an analyst, you log on to the thing. You enter in information about, okay, it's today, and this is sort of the position on Mars that we're concerned with, and then you get these query results back. So each of these cards is corresponding to one particular satellite passing overhead at a particular time. This information in the upper left is showing which satellite it actually is, kind of what time of day the satellite is passing at. The information in the bottom left is showing kind of, okay, we see it in the east or we see it in the west. And there's some buttons which allow you to kind of change the display of the polar plot, so you can change it between polar coordinates and rectangular coordinates if you're more comfortable with that, for example. And then the polar plots basically just explain what you're seeing there. Those differ. Yes?
Why wouldn't you just put them in GSM coordinates? That's the most natural coordinate system for
Right. So there's basically there's like a lot of legacy to this that I'm kind of skipping over. The thing has been up there for like 13 years, and so there's all these things that we have to work within because of the way that the models of the data transfer works. We have a lot of constraints around that.
But that would be the ultimate goal.
Oh yeah, I mean given like all the data that we could want in the world, there's other ways to do this, but yeah, given these constraints, this is what we came up with. Okay, so then at the top here, you have kind of some controls. You can sort of filter, toggle on and off the predictors if you want to see some more information about that. You can sort of change the size of the charts themselves and change your orientation. And then there's this selection, or there's this interaction that you have as an analyst. You can say, okay, I know that I'm interested in one particular heading. And you can sort of click and drag with your mouse to select data points at a particular heading. And then this list on the right populates. And so each of these rows on the right are corresponding to basically one slice of one of these pies that you're seeing. So the numbers on the right are corresponding to which satellite it is, and then these data points in the middle are corresponding to your purple and red estimates. And then there's some more controls at the top that kind of show they allow you to sort the list by varying things. They allow you to sort of save particular points for future investigation and send it along. And so the system was developed over a period of 10 weeks. We did field user research with 4 spacecraft operations engineers. which as researchers is kind of not very many people to work with, but there's only actually 4 people who do this job total. Basically, we derived this set of principles, sort of going through all these prototypes that we built, and sort of coming up with sort of things that you should be thinking about, or we thought to also looking at other systems that were kind of in a similar space. And I'm going to kind of skip ahead here. But basically, there's this list of 7 principles that we think kind of are important if you're thinking about these things. This is a link to the paper. It's open access, so you can download it and you can see, kind of dive in more to the work specifically. This is me, and my two co-authors are in the back here who helped design this and did a ton of great work in terms of design. So with that, I wanted to say thank you.
Est-ce qu'on a des questions pour Mathieu? On a des gens ici qui ont fait des tableaux de bord des fois, et qui ont aussi été contraints par les habitudes et les conventions. Oui,
I'm curious, was there, how can someone make a call of investing 10 weeks in designing a dashboard versus 10 weeks in trying to automate the solution to this problem? Like, are there some guidelines around that? Because it's like, is that not a call to make in this case? Or?
Yeah, so there are so many different considerations that go into this, and the people who are using the system, like there's only 4 of them in the world who are like qualified to make these decisions because they have years and years and years of training. So this is not something that we even like really considered trying to do an AI system. Like part of some of our early ideas were like, oh, like we know what the highest estimates are, right? We know what sort of like maximum likelihood to optimize the total expected value transferred, but because there's all sorts of other considerations that aren't totally reflected in those numbers, we need a human loop.
Yes. How do you assess the benefit of each of these particular sectors? I don't know what you're measuring. Are you measuring magnetic field? Are you measuring thermal properties?
So that is like megabytes of data.
Megabytes of data?
Yeah.
So it has to do with the communicability. There's nothing to do with the favorable directionality of the sector.
It's the direction of the rover, yeah.
Okay, very good. Thank you, Matthew. You literally have an astronaut tattoo here. Did you get it from them? This is how you got the job, right?
Yes.
Thank you so much, Matthew. We're going to move on to the next one.